All right, good morning. Let's wrap up. Well, not wrap up. Let's continue with MOSFETs. A couple of announcements. So the my material and notes were from an older edition of the book, right? So there is a mismatch with the chapter number, sorry. FETs was chapter 5 in the current edition and before in the older one. And so I just flipped them in the class notebook again just to avoid any confusions. At the student end, there's not much difference. Okay, the notes and everything is still the same. It's just that, it says chapter 4 versus chapter 5. That's all. So let's see. Class notebook. We're talking about the device operation for a MOSFET. We looked at a MOS capacitor or the gate. And channel established and current was flowing. So when the channel is established in the MOSFET, which is right here, that's the channel. Now, if we apply a voltage between the drain and the source, we expect current to flow through because there is a pathway that connects both the source and the drain. Okay, there's a pathway that connects both the source and the drain. Now, unlike the FET, a voltage must be applied at the gate to create this channel. Hence, this is known as an enhancement mode device. So this is an enhancement mode MOSFET. Okay, enhancement mode. There are depletion mode MOSFETs also, where a channel is already created during the manufacturing process. So similar to the FETs, like the JFETs, the junction FETs, a negative voltage or a voltage must be applied at the gate to turn the channel off. So those will be known as depletion mode MOSFETs, where the channel already exists. It is created during manufacturing process. Here, applied voltage creates the channel. Without a channel being present, the two regions, the drain and the source, would not be connected. There would not be any current flow. Okay, so no matter how much VDS you apply in this device, if there is no gate voltage, it will not turn on. Okay, so voltage, positive voltage must be applied in order for the device to turn on. All right, so we apply VGS, inversion occurs, N channel is created, N channel links both the drain and the source. Now there's a clear pathway between the drain and the source. The device is in a state of readiness. Now, when you apply VDS and increases slightly above 0, current will start flowing through the channel. So electrons are moving in response to the electric field due to the applied voltage between drain and source, VDS. So VDS now is slightly above 0. Okay, current starts flowing. Okay, electrons are moving from the source to the drain. Current moves from drain to the source. So ID is flowing. The relationship between the applied voltage VDS and the resulting current of ID is linear. So linear relationship, and these are varying values of VGS. Okay. And hence this is known as the linear region of operation. What device or what component has a linear relationship for voltage and current? Resistor. And hence the MOSFET behaves like a voltage controlled resistor. Depending on the applied voltage, we can force the MOSFET to operate in the linear region. Hence, voltage controlled resistor. Okay, it's a voltage controlled resistor. So far, so good. Yes. Yes. So we always take, well, there's two different kinds of circuit analysis you can base on electron flow and hole flow. So there are textbooks that talk about electron flow versus hole flow, like circuit analysis using hole flow, circuit analysis using electron flow. Typically, for everything that we do here in North America and most parts of the world, we talk about flow of electrons, and then we say the current always flows opposite the flow of electrons. So in a MOSFET, the electrons are moving from the source to the drain, and hence the current is actually flowing from the drain to the source. It's always opposite to the flow of electrons. Your earlier circuit analysis classes or physics classes may have mentioned this, have they? Right, opposite of electrons. So again, and we pick the terminal and say this is the source and this is the drain, but it's a symmetrical device. If we applied a positive voltage at the source and a negative at the drain, electrons would flow in the opposite direction. So now current would be flowing from the source to the drain, but we wouldn't call it the source anymore. We would call it the drain because the electrons are being sourced from the other terminal. Does that make sense? The terminal is called the source because it is the source of electrons. Because we are applying negative at that terminal and positive at the other terminal. So positive is the drain, negative is the source, hence VDS. And so electrons will now drift in response to the electric field attracted by the positive charge of VDS, and current flows from drain to source. Theoretically, it should still work. If the fabrication process is symmetrical, it should still work. Was that the question you had? Theoretically, yes. Yeah, if it's symmetrical, yes. So the points being made are, if the device is symmetrical, can we simply flip it and call the drain as the source and vice versa? And the answer is yes. It will still work. Yep. All right. Let's see. Oh, so linear region, right? The linear region is also known as the triode region. Going back, vacuum tube triodes, right? You had the first vacuum tube had two electrodes, anode and cathode. We had current flow between the anode and the cathode. Then we inserted a third electrode in there to control the flow of current, right? Hence, that's where the name comes from. Okay, so it's known as the linear region or the triode region, where the current, the output current ID, has a linear relationship with the applied voltage VDS. Okay. There are a few parameters that I'd like to present. The first one is the equation for the current. Now, in the FETs, the MOSFETs, we have the drain and the source, right? The two terminals. Current flows between the two terminals, and then you apply a third terminal like a gate to control the flow of current between the two terminals. The gate is electrically isolated from the rest of the device. Technically, it's not even part of the device, right? The device is a substrate, and you attach a gate afterwards, right? The gate is deposited as a metal on top of that substrate. Isolated electrically. So what does it mean for the gate current? If it's isolated electrically, what does it mean for the value of the gate current? Zero. And because of the oxide, gate current is zero. Also, and that of course applies for DC gate current. Okay, so actually this would be more technically accurate. Okay. The input impedance, the input resistance at the gate is infinite because of the oxide. And of course, real life MOSFETs, it's not quite infinite, but it's a very high value, yeah, in the mega ohms range. So we can write the drain current and the source current are exactly the same. ID is equal to IS. And we can write an expression for ID in terms of the device parameters, the device physical parameters, and the applied voltages. So ID can be written as Kn prime W over L. Those are the physical dimensions. And the applied voltage is VGS, threshold voltage VTN. The threshold voltage again depends on the physical dimension of the device, where we can describe Kn as Kn prime W over L. And Kn prime is the permittivity of the N-type material and the capacitance of the gate oxide. Again, that goes back to the manufacturing process and the design process. So the quality of the oxide and the dimensions of the structure. Now, VGS, VDS are the applied voltages. VTN is the threshold voltage. Again, the threshold voltage is the voltage that is applied at the gate to invert the channel and create a pathway between the two N regions. Okay. So that also depends on the design and the manufacturing. Kn and Kn prime are known as the transconductance parameters. Okay, with units of amps per volt square. amps per volt square. Transconductance Gm is ID or VD, sorry, ID or VGS. Is the input voltage and the output current, hence transconductance. Okay, transfer characteristics, transconductance. And you can plot this at the Q point. There's one more quantity, and that is the on resistance. On resistance, R on. And R on is the reciprocal of Kn, actually, just write Kn VGS minus VTN. Okay. Graphically, of course, we can find it from the values for VDS and ID. Okay. This applies only in the triode region. The triode region. All right. So we applied gate voltage, we created a channel, then we applied a drain voltage so that the electrons can flow from one terminal through the channel to the other terminal. But then what happens if you keep increasing the drain source voltage? In a JFET, we saw that if you keep increasing the drain source voltage, the two depletion regions end up meeting and the channel pinches off. So here, something similar happens. The cause is not the same as the JFET, but the resulting effect is the same. The channel that was created pinches off after a certain level of voltage. Okay, and then we reach a operation region known as the saturation region. So here we have the channel, right? You have the channel, electrons moving in this direction. VDS applied is small value, just enough that current flow starts. Now, remember, this is an enhancement mode MOSFET, meaning a external voltage is applied 0, 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth. So external voltage is applied to create that channel, right? Threshold voltage is the level of voltage that is required to just create the channel, right? That's VTN. That's basically inversion process. So threshold voltage is the voltage where the inversion happens, and then VGS is at a higher level. So when VDS reaches the level where the difference of VGS and threshold voltage are equal, a voltage exists between the drain and the gate. And because of the effect of this voltage, the channel begins to pinch off. Or begins to close. Okay, it begins to close. Let me draw with a different illustration. This is, of course, not to scale. drain, source, and the gate. Gate, of course, is not in the middle, but I just want to illustrate something. You have voltage between the drain and the source, and you have a voltage between the gate and the source. This creates a voltage VDG between the drain and the gate. And so with increasing drain source voltage VDS, this causes the channel to close off. And at one point, when VDS is far greater than VGS minus VTN, it is completely pinched off. Right there. Completely pinched off. VDG, all right, as VDS minus VGS. And when this pinch off occurs, similar to the JFET, we would expect it to go to 0, but it doesn't. What happens is this. For some high level value of VGS greater than 0. What happens at the channel at pinch off is the electrons that are were flowing in response get pulled, all injected into that depletion region. So right before it pinches off, the electrons were flowing at a steady rate, right? It was rising in a linear fashion. But once the channel pinches off, the electrons are now pulled into the depletion region. And because of the positive voltage applied at the drain, are attracted to the drain, and they are pulled and swept out towards the drain. So current still keeps on flowing, but now it does not have a linear relationship. It saturates at a level, and hence the region of operation, saturation region. So even though the channel is pinched off, electrons are still flowing through there. Remember, current only flows due to the presence of charge carriers or freely moving charge carriers. The depletion region has a negative charge, net negative charge, because of the immobile acceptor atoms or the immobile acceptor ions. So it has negative charge, but they are not free to conduct. They are not free to move about. Electrons from the channel cross over into the depletion region. So now there are free charge carriers or charge carriers that are free to move. And because of the positive forces of attraction at the drain, the electrons are pulled towards the drain and current is still flowing the MOSFET. However, it's now pinched off, so the level is at a constant. Okay, so the level remains constant. So the operation and the cause of the pinch off is different than the JFET, but the result or the resulting effect is exactly the same. Current still flows to the device, but it saturates at a high level. Okay, saturates at a high level. If VGS is removed, there is no channel and there is no current flow. It's cut off because channel does not exist. Okay, so no matter what voltage you apply, there is no current flow. Okay. Doing on time. Any questions? No. Okay. Well, let's look at the different symbols of the MOSFETs. I don't know if I stated in this section or not, but we used to have MOSFET experiments in 346, and then they moved it from 347 to 346, and then when 347, they did some reshuffling, and so MOSFETs experiments were reshuffled back into 347. So you'll be doing a lot of MOSFETs next quarter. Yes.
Oh, I have a question on the previous slide, actually. So I was doing some reading online, and it said during the saturation region that it acts almost like a current source. Is that true? It's just stuck at that current level, right?
Yep. The question being asked is, like the JFET, does it act like a current source? The answer is yes. Because a source, whether it's a voltage source or a current source, is exactly the same unit in real life. A voltage source is a power supply that supplies voltage at a constant level, but the current changes depending on the requirements of the load. And a current source is a source that supplies a constant level of current, but it changes the voltage depending on the requirement of the load. So current sources and voltage sources in real life are exactly the same. We can't have one without the other. We cannot supply voltage without supplying current. We cannot supply current without supplying voltage. So current source and voltage source, the difference only is that a voltage source is constant value of voltage, current source is a constant value of current. So anytime we see something like this, constant value of current, the device is working like a current source. Same thing with the JFET, because it saturates at a level, so constant current source. So it behaves like a resistor in the linear region and a current source in the saturation region. And also, one important point is all of this is exaggerated, right? In real life, these devices are on the size of nanometers, very, very small. Okay, very small. Okay, so several different kinds of symbols for MOSFETs. I always like to tell students to focus on the 4. Okay, so what have we looked at? We have studied or looked at N-channel MOSFETs or NMOS transistors. And because a voltage must be applied to create or enhance the channel, we call these as enhancement mode devices. Okay. Similar to the NMOS, we have the PMOS. We have PMOS enhancement mode. And then, like the JFET, which are depletion mode devices, we can pre-build a channel into the MOSFET during the manufacturing process. And so if a channel already exists, now we need to apply a voltage to turn off the channel, not to create one. And so those are known as depletion mode MOSFETs. And so we have both NMOS and PMOS of the depletion mode kind. So here's how you remember these. There are 3 terminals, drain, source, and gate, right? Drain, source, and gate. There's a 4th terminal added for the bulk or the body of the substrate known as B. Remember from the early slide? B that connects to the body of the wafer. So if you have an arrow pointing into the device, it's an N-channel MOSFET. If there's an arrow that is coming out of the device, it's a P-channel MOSFET or a PMOS. Again, arrow pointing in, N. An arrow pointing out, P, or PMOS. Okay, that is true whether it's enhancement mode or whether it's depletion mode. Okay, so here is enhancement mode N channel, and here it's depletion mode N channel. Arrows are pointing in. Okay, arrows are pointing in. Now, the enhancement mode versus the depletion mode is if the gate is indicated by a straight single line versus 3 lines or 3 dashes. Depletion mode devices have single lines right here. Enhancement mode, 3 lines. Okay. When I was a student, I like to remember it as the E, the letter E has 3 prongs. So 3 dashes, 3 prongs in E, enhancement mode. Okay. As for 3-terminal transistors is a little bit different, but again, you'll spend the rest of your academic career working with a lot of MOSFETs and BJTs. You'll have a lot of time to get familiar with these. Okay. JFETs, I mean FETs have flat lines like this. Yeah, this is something I'm going to point out when we look at the next chapter, which we're going to do in just about a minute. Okay. So again, FETs and MOSFETs are something that you would look at a lot in 307 and also 308. We build a lot of circuits using MOSFETs and BJTs. But for now, I'd like to turn our attention to the next topic, and that is bipolar junction transistors. The rest of the this course deals with bipolar junction transistors. So answer me this. An FET is blank, blank, blank device. Unipolar, nonpolar, bipolar, or tripolar? It's a what? FET, yes. You asking or stating? It is a unipolar device. The polar in this case stands for, and I've mentioned this earlier when we were doing diodes, basically how many charge carriers or what kinds of charge carriers are involved in current flow. FETs, whether it's MOSFETs or junction FETs, it's only electrons or holes, only one type. For diodes and for junction transistors, it's both electrons as well as holes. Hence the term bipolar. Okay. Both kinds of charge carriers, electrons and holes, are responsible for current flow in these devices. Okay. These are, even though the name is transistor, it's completely different construction and completely different principle of operation from the field effect transistors. Okay. Bipolar junction transistors or BJTs are created from 2 back-to-back PN junctions. Okay. The third terminal is part of the device structure. It is not added on separately like a FET or a MOSFET. Okay. So a BJT is essentially 2 PN junction diodes connected back to back. If the common region is N, then we have a PNP transistor. And the common region is P, then you have an NPN transistor. We will primarily look at the NPN transistor. Okay. The symbol for a MOSFET with straight lines, where a symbol for a BJT is angled lines. If the arrow is coming out, it's an NPN transistor. If the arrow is going in, it's a PNP transistor. Okay. This is indicating the direction of the current flow. Yes.
For each diagram, there's like a circle around one of them, and the other one doesn't have a circle.
So it's just an illustration where some authors might use a circle around it. I haven't seen many, to be honest, but it's just something I like to show students. It's in one of the different books. Yeah. Okay, so the three terminals are very similarly called to the FETs. You have drain, source, and gate. Current flows between the drain and source controlled by the gate. So for a BJT, it is a collector, emitter, and the base. Okay, collector, emitter, and the base. Source, emitter, drain, collector, gate, base. Okay. The next few slides. If you've noticed your lab kits, you have actual JFET devices with a black epoxy packaging. This is a slice of a transistor. Model number is 3904, 3904. The actual transistor is right here. And that's not even the actual transistor. These are the thin leads that are used for connections. Okay. Thin lead used for connecting lead. Here's a close-up of that device. The actual transistor is right here, probably in the few microns at the top. If this was a 500 micron wafer thickness, it'd be like with one or few microns at the top. It's a gold bond wire to make connection with the emitter. And the backside, we are making contact with this huge metal plate. Yeah, I have to thank Professor Chuck Bland for these slides and these images. Next slide, I have a close-up view, for like a top view of a integrated circuit transistor. Okay, integrated circuit transistor. All right, so let's see what an actual physical construction looks like. So we said it's two back-to-back PN junctions, right? But the key point is in the differences of the construction. So we have a N-type material. So this is an NPN transistor. So we have an N-type material, and then entire material collector is the biggest in size or largest. Okay, it's the largest structure in the device. It encapsulates both the emitter and the base within its region. Okay. Emitter is the smallest. And then there's the base, which is the thinnest. It's very, very thin. And this is the most critical aspect of operation. Okay, so that's physically speaking. Electrically speaking, the base is very lightly doped. So there are not very many charge carriers available for current conduction. It's very lightly doped. Collector is average doping. Whereas the emitter is the most heavily doped of the three. Meaning there are there's a plurality of charge carriers that's available to conduct charge. Okay. The emitter-based junction behaves like a true diode because we forward bias it. And the collector-based junction typically might be reverse bias or it could be forward bias. Okay. So this is from the side. Let's look at a three-dimensional cutout, a BJT. So here's the collector region. This entire region that you see here is the collector region. It's an NPN transistor, so the collector is N-type material. The epitaxy refers to the fabrication process. So it's an N-type material created using the epitaxial growth process. Okay, so don't worry about that. If you take 434, or sorry, EE 420, 423 or 424, EE 423 fabrication, that's where you can learn about epitaxial growth of silicon. Then so the collector basically is the entire substrate. Okay, the entire substrate. And you see an N plus region underneath right here, which says collector. That N plus region is again from the fabrication process. It provides a good ohmic contact with the N-type material below it and the metal conductor above it. There's like an interface between the two. Okay, that's what it's doing. And then you have the base, and then you have the emitter. Now, you see that the emitter is labeled as N plus. The plus means it is highly doped compared to the other two regions. Sometimes you will also see this. You might see an N plus, a P, and an N plus plus. So it's showing, all it's showing is the varying levels of doping. It's showing that the P-type region that forms the base is lightly doped. The N plus is more heavily doped compared to the P region. And the N plus plus is even more heavily doped than the N plus region. So the plus signs, all it means is it's visually indicating the level of doping in those regions. Okay, that's all it means. Make sense to everyone? Okay. All right. Then, as I was saying, we have two back-to-back diodes, but they do not always behave like diodes. There are different modes of operation. There's actually 4 modes of operation, but 3 of them are the most important. And they depend on the external biasing. The external biasing is basically VCC and VBB. This is between the collector and the emitter. This is between the base and the emitter, or applied at the base and the collector, respectively. The resulting currents are called or labeled as IC, IB, and IE. And then the voltages are measured with respect to the emitter, so VCE and VBE. Okay, so we have current flow from the collector to the emitter. The emitter is the one that emits the electrons. Current flows in the opposite direction, so current flowing from collector to emitter. Similar to the FETs, we have current flow between 2 terminals, and then a third terminal is controlling the flow of that current. So in this case, the third terminal is the base IB. Hence, IB controls IC. For a FET and for MOSFETs, the gate current was 0. Here, IB is not quite 0, but it still is very small. And typically, it's in the microamp range. The ratio of IC and IB is known as beta, and it's the most important parameter for a BJT. Most important parameter. It is specified on the spec sheet. Also, there are a range of values for beta. And the reason is that the manufacturing process is not precise. So even if you manufacture two transistors side by side, separated by just a few microns on the exact same transistor, on the exact same wafer at the exact same time, they can have they will have two very different values of beta. The reason is very simple. We are implanting millions and billions of atoms in there, not even millions and billions, 10 raised to 15, 10 raised to 16, 10 raised to 18 atoms per centimeter cube. You'll remember from chapter 2. So we cannot control the fabrication process down to the last single atom. And so there's always going to be variations in the exact same device. Okay, that's the most important parameter. There are circuits that we design so that the varying parameters do not have much of an effect on the rest of the circuit. Okay, and that depends on the biasing that we create. Yes.
So you can like for the manufacturing process, so you can't control how much the each component would get. But would that mean you would just make like a bunch at once and compare which ones are similar, or is it just like within an acceptable range type of thing?
So the question being asked is, how would we work with these devices, right? So the answer is yes, we can control the manufacturing process to a certain extent, but when we are talking about 10 raised to magnitudes of like 10 raised to 17, 10 raised to 18 atoms, we can control it down to a certain level, but not beyond that. We cannot control it down to like every single atom. So if you're implanting 1 into 10 raised to 18 atoms and 1.00001 10 raised to 18, there's going to be a slight variation in the device. And so it's an acceptable range. Even in your JFETs, when you all did the pre-labs, you would have seen range for pinch-off, VP. There was a range given. The reason for the range is because you cannot manufacture it exactly the same. Okay, so when we look up the spec sheets, all of these not material properties, these parameters that are specified by the manufacturer, they'll always have a certain range, and that is because of the variations in the manufacturing process. Okay. All right. So beta is defined as the current gain. It's again the most important parameter on the spec sheet of a BJT. And then we can write an equation for IE and VCE. IE, the emitter current, is the sum of IC and IB, and VCE is the sum of VCB and VBE. What is the value of VBE? If it's a forward bias junction between the base and the emitter, what would be the value of VBE? Should I go back and change your quiz grades? It's a forward bias PN junction. Seriously? The forward bias PN junction, if it's made out of silicon, is 0.6 to 0.7 volts. That's one of the things that you will use when you analyze circuits based on BJTs. Okay. One last, well, actually, you know what, the bell's ringing, so let me just stop right here, and then we'll pick up here again on Friday. Monday is a holiday, so no class on Monday, but Tuesday and Thursday is the same lab. BJT is the longest lab, so I want students to prepare in advance. Also on Friday, I might, the 50-50 chance I might either teach online or I might post a recorded video. I'm going to post one for Monday anyway. Okay, I'm going to post one for Monday anyway. Monday is a holiday, academic holiday. So I'm planning to post a video for Monday, but I might post one for Friday also. Yes.
quiz, but we should watch a video on.
Yes, quiz will be on Wednesday. That's going to be the next point. Yep. I'll be working all through the long weekend. So I'm going to make you work too. Yes. Go ahead. I'm listening. I'm listening.